Oh, it's about that time. We got rectangles. Rectangles coming up here in honors geometry. Everybody loves rectangles. They're one of my favorite quadrilaterals. So let us begin, indeed. All right, to add to our, we'll call it family tree of quadrilaterals, we're going to have a couple more properties. All right. First one, same as a parallelogram. So everything that happened in a parallelogram happens in a rectangle. Opposite sides are parallel. Opposite sides are congruent. Diagonals bisect each other. All sorts of good things. Opposite angles are congruent. Awesome. But we also have diagonals congruent. Diags congruent. So if rectangle, diagonals are congruent, or diagonals are congruent, then it's a rectangle. You see, that can work both ways. And then lastly, we have 4 right angles. Again, these will be done as if-then statements. So if it's a rectangle, then diagonals are congruent. If it's a rectangle, then you have 4 right angles. Or you can go back the other way. Let's use it. Alrighty, so we have proved that the diagonals of a rectangle are congruent. That is one of our properties, but we can prove that the diagonals are indeed congruent. I'm going to draw a rectangle for you real quick and label it A, B, C, D. And let's draw in a couple diagonals. Call that E. So basically we want to prove that AC is congruent to DB. All right. Now, I'm not going to actually work the proof, but we're going to show that they are indeed congruent. All right. Well, if it's a rectangle, I get everything from a parallelogram, so I get my opposite sides congruent, right? That's awesome. That's lovely. Let's see here. What else do I have? I'm thinking that I want to maybe go with a couple triangles here that overlap. Like if I got this triangle congruent to this triangle, well, I'd have a reflexive side. That's good. And if I can prove these two to be congruent, then I can get AC congruent to DB by CPCTC. Well, what else do I know about a rectangle? Again, I can't use that the diagonals are congruent because that's what I'm trying to prove. But I do know that I've got some right angles. And what do we know about all right angles? All right angles are congruent. I've got side, angle, side going on here for these two triangles. That's how I would end up proving them congruent, and I can get my diagonals congruent from there. If you want to see the actual proof worked out, take a look at the notes keyed. They are on this page off to the right-hand side. Lovely. Let's move on. All right, in this example here, we got circle O. Sometimes the way that this imports into this program, it doesn't work well. So that's circle O. And then it says OACD is a rectangle. Then I got some lengths. It says OA is 5, AB is 2, and we want to figure out what AD is. Well, I do know that in a rectangle, my diagonals are congruent, right? So DA, and if I drew in OC, those two should be congruent because it is a rectangle. Well, what's OC? OC is actually a radius of that circle, and OB is also a radius, which is 7. And I know in a circle, all radii are congruent, so that would have to mean that OC equals 7, right? Because it's a radius. OB is a radius, OC is a radius, so they're 7. And since OC is congruent to DA, I know that their lengths are the same as well. So, or AD, I guess. AD equals 7 then. Perfect. So not only did I use radii are congruent, I also used the diagonals of a rectangle are congruent as well. Alrighty, once again we have a typo. This should say x squared minus 1, not x2. Alright, so it says RSTU is a rectangle. Find RT if ZT equals x squared minus 1 and UZ equals 3x plus 9. Alright, so we know that the diagonals of a rectangle are congruent. We know that they bisect each other. We're dealing here with diagonals, right? It wants us to find RT, which is a diagonal. I know ZT is x squared minus 1, and I know UZ is 3x plus 9. All right. Well, if my diagonals are congruent and I bisect both of them, what property would tell me that those bisected parts are congruent. That's a throwback to division property, right? Bisect, bisect. We would get UZ and ZT congruent to each other, right? Why don't I just mark them with congruent ticks? Boom. These guys are going to end up being congruent. So why don't I set them equal to each other? X squared minus 1 equals 3x plus 9. Oh, this is wonderful. I've got a quadratic that I'm dealing with, which means I get to factor. My favorite F word, you know? It's just wonderful. I see this problem like, factoring. Yes. All right. So what multiplies to negative 10 and adds to negative 3? That would be negative 5 and positive 2. Lucky for us, it does factor. Otherwise, we'd have to use the quadratic formula. And that's just a whole bunch of wonderful stuff. All right. So x equals 5 and x equals negative 2. Now, I've got two solutions here. I do need to make sure that it works in the context of the original problem. A lot of times we're like, negative for x, that's no bueno. But if it works in the original, we're good. All right, so if I plug in 5, what do I get for each one of these? I get 25 minus 1 is 24. I get 3 times 5 is 15 plus 9, which is also 24. So both of those are 24 and 24. So the total RT equals 48. But what about with the negative 2? If I plug in negative 2, I'll do that one in blue. Negative 2 times 3 is 6, or negative 6 plus 9 is 3. And then here would be negative 2 squared is 4 minus 1 is 3. That checks out as well. So the entire length of RT is 3 and 3, which is 6. All right. So RT could also equal 6. How wonderful is that? But you might be saying, wait, Mr. Allen, how can this thing equal two different things at the same time? Well, it doesn't. Or just saying with this information of UZ equaling 3x plus 9, x squared minus 1 for ZT, with that, there's two different possibilities as a length of RT. Okay? Lovely. All right, so we want to give the most specific name for the quadrilateral BGHL and justify our answer. So as I stated yesterday's video, we're going to want to look at slopes for the most part, and oftentimes it comes down to our diagonals as well as our sides. So let's do that. Let's see here. If I were to show that, let's see, how about BG? Let's find that slope. That would be up 1 to the right 2, so 1/2. And then LH is up 1 over 2, so that's also positive 1/2. Those are parallel, so that's great. Let's see about GH and BL. GH, I would go up, it looks like 6, and over to the right 3. So 6 over 3 is 2, but it is negative, right? Up 6 and to the left 3. Did I say to the right? I'm crazy. All right, so up 6 and to the left 3, left being negative, so negative 2. And then we have from L to B, we're going up 6 and to the left 3, so that means it's negative 2 when simplified as well. So my slopes on my opposite sides are the same, which means that we have opposite sides parallel. So it's a parallelogram. But could we be more specific? Well, if I look at my slopes on my consecutive sides, I have 1/2 and negative 2. Those are opposite reciprocals. Therefore, my consecutive sides are perpendicular, meaning they form right angles. So we have ourselves a rectangle. Okay? Yay. And we could say in there 4 right angles, perpendicular sides, opposite sides, parallel, all those kinds of things make that into a rectangle. In the future, we'll start looking at if it's a square or a rhombus or a kite, and we'll look at those diagonals. All right, but for now, with what we have, that's really all we need to show that it is a rectangle. Okay?